We are going to continue looking at developments in CPU design. This morning we talked about adding in extra features to make the CPU do many different things, usually in response to the software people who call the architects to ask for extra features to be added. Here we're going to talk about making CPUs go faster. So this is keeping the instruction set the same, so we're not going to present new features to the user. The interface will look exactly the same, but we're going to try and accelerate how the instructions get executed. So there was a time when the easy way to do this was just to turn up the clock speed, or equivalently assume that the fabrication plants would magically get smaller and faster every 18 months or so. That was Moore's law for clock speed. It's no longer possible to do that. And so you'll find in general the thrust of architecture now is about doing things in parallel. We still have this form of Moore's law for transistor density. We are still making fabrication technologies get smaller and smaller, so we're down to just a couple of nanometers now for a basic feature. As transistors get smaller, that means you can fit more of them onto the same piece of silicon. And we can't clock them any faster, but we can exploit the fact that there are more of them. Basically, that means building a CPU that does things more cleverly. We can put in more digital logic to try and get speed, either from parallelism of execution or from doing extra calculations to help change the computation to make it go faster, maybe to optimize computation or to figure out which things we can do simultaneously. So we'll have a whole lecture on parallel systems in general later on. This is called instruction level parallelism, and it means the type of parallelism that is invisible to the end user. It means the end user is still going to give their program as a series of instructions. It's still a serial program, but the way that we execute that series of instructions internally is going to start doing things in parallel. That means doing a bunch of things simultaneously by taking advantage of the more silicon that is available. So this is called ILP, or instruction level parallelism. Okay, so here's the Manchester Baby implementation that we saw last time. And you remember it's all driven by clock cycles. The clock drives a counter. This is a 3-bit counter. And that counter keeps track of where we are in the compute cycle. So a 3-bit counter has 8 distinct tick states that come out of this decoder. At each one of these ticks, something different happens. And roughly that corresponds to the fetch, decode, execute cycle. So we saw, for example, at tick 0, that's where we update the program counter. At tick 1, we start the fetch. We hit on the RAM, we bring something into the instruction register. At tick 2, we store it in the instruction register. Then we decode it. And then from ticks 3 to 5, roughly, we do the execution, depending on what the instruction is. Now, you will notice that most of the digital logic here spends its time sitting around doing nothing. Most of the digital logic here is only activated at one of those cycles, okay, at one of the ticks within a clock cycle. So, for example, the arithmetic in the Baby, there's only a subtractor. Okay, in a modern CPU, there's going to be a huge arithmetic logic unit capable of doing many different mathematical operations. But the ALU is only active at one of these ticks, and for the rest of the time, it's just sitting there doing nothing. Right. So this thing gets enabled at tick 4. All this logic here around updating the program counter. So this is effectively the main control unit. Right. Normally it will increment the program counter, but it's also thinking about jumps and skips. all of this stuff only comes on at tick 5 and tick 0. You might wonder if it's possible to keep more silicon in use all the time. Okay, so in this design, if you actually run this in Logisim, you'll see different parts of it light up at different clock ticks, right? You'll see there's like a flash of activation here, and then it goes here, and then it goes here, then it goes here, and the rest of it's sitting around doing nothing. So you might wonder if we can make things more efficient by trying to do more than one thing at the same time, right? So in particular, in this implementation, the problem is especially bad because we started with an 8-tick clock cycle. Now you notice we only use ticks up to 5. Yeah, so we're not even using tick 6 and 7. If, for example, we could do some of the work from ticks 4 and 5 at the same time as some of these other ticks, we might be able to get it down to a 2-bit clock cycle. Okay, that would actually make the whole thing run twice as fast. Yeah, we could get a 2 times speed up just by getting work out of 2 of those ticks and running it alongside some of these things. So for example, at the end of the fetch, decode, execute cycle, we update the program counter, and usually that just means adding 1 to it, but we're taking a full tick to do that. So you might say, why not work on updating the program counter while we're doing the arithmetic? Yeah, we might assume that most instructions are not skips and jumps. Most instructions are just going to go to the next line. So we might as well start work on this while we're doing some of this decoding and some of this arithmetic. Or you might even consider hitting on memory to fetch the next instruction, right? You might be working on your arithmetic, or maybe you're even working on your control flow. You're saying, was this a jump instruction? Was it a skip instruction? What do we do with the program counter? While you're doing all that, you might even go and hit on RAM and fetch the next instruction so that it's ready when you want to do it. And if we could find a way to combine work from just 2 of these ticks, we could make the whole thing go twice as fast by getting down to a 2-bit cycle. So this is called pipelining, okay, or instruction pipelining, and it's a form of instruction level parallelism. And the image to have in your head is of a production line. Okay, here's a factory making, I don't know, bits of iPhones perhaps. And you can see in a production line, you don't just take a single iPhone and give it to one person and have them pass it to the next person and the next person. What you do is you work on a whole bunch of iPhones at the same time, and they all flow down the conveyor belt. And each phone, so each phone is like an instruction from your program. Each phone or each instruction is getting processed at a different step of processing at the same time. So you might, for example, consider 4 workers on a production line, and they're each processing a different instruction. So imagine your program flowing down this production line, and each instruction can be split into several stages, and people argue about exactly how to carve them up. Usually they include fetch, decode, and execute. You might also see this write back stage. So part of execution arguably is storing the result, either sending something back to memory or sending to a register. Sometimes that's extracted from the rest of execution. So execution might just mean doing the ALU, and then when you get the result of that, it's either going to go in a register or in memory. You might stick it in a separate phase here. Or you might carve up the execution cycle in some other way. So a modern CPU has around 37 stages that are recognizable as being carved up. Interestingly, pipeline stages don't show any clear size trend over time. So early pipelines were just fetch, decode, execute. Then you got this 4-stage one and maybe 5-stage one. Around about 2000, they grew to this size, and there's no clear trend of getting bigger or smaller. Sometimes pipelines get longer, sometimes they get shorter since then, depending on the decisions made by the architects. So let's consider a 4-stage pipeline, considering a fetch, decode, execute, and write back. And you could imagine each of these workers. This worker would be doing fetch, decode, execute, write back. They're processing 4 instructions in a sequence in your program. Okay, that's 4 instructions are running through the system, looking like this. So at each tick within the clock cycle, you can see what is the state of these 4 instructions. Okay, here all 4 instructions are waiting to be executed. At tick 1, the fetch part of the first instruction has come into the system to get processed. Okay, at tick 2, that instruction has been fetched, and now the decoder starts its work on the green instruction. And at the same time, the next instruction can be getting fetched. Okay, while we're working on the decode. So in terms of the baby, you've hit on RAM. RAM did its work to bring in the first instruction into that instruction register. On the next tick, we're going to send it onto the decoder. While we're doing that, we can have the next instruction getting fetched. Yeah? So in particular, no one is using the RAM while we're doing the decode. Okay? Decode does not require RAM access. That could be a problem if you were doing something else that required RAM, because you can only hit on RAM once at any given time. So on the third tick, the green instruction is now getting executed. So if it's arithmetic, that means it's been sent to the ALU. The purple instruction has now reached decode, and the blue instruction is now being fetched. Okay, so that's 3 lines of your assembly language or machine code program all getting processed together. When we get to the 4th instruction, we've now got 4 instructions all getting processed together. So the green one's nearly finished. It's got its results from the ALU, whatever. Those are now being written back to wherever they're meant to be going. Purple one is now getting executed. That means we're keeping the ALU busy. The blue one's getting decoded. That means we're keeping the decoder busy. And this red one, the 4th line in the program, is now starting to be fetched. So you can see that the program will propagate through the system, and you've got 4 workers all running on it together. Those workers roughly correspond to the tick cycles, or the work that is done in a tick cycle. So we're going to take something like this original baby design, and we're going to say in tick 3, instead of just activating this stuff, we're also going to keep the decoder going, and we're going to keep the fetching system going, and we're going to try and keep all the silicon in use together. Okay? So in some cases this works really well, and in other cases it works not so well. So can anyone see where the problem is going to be with this approach?
If the instruction has like branchings, so it will cause issues. You have to jump.
Yeah, brilliant. So this works beautifully in an application like signal processing. Okay, if you're building a CPU to go in a television and it's going to run a multimedia codec, it's going to decompress MP4 data, that kind of thing. In signal processing, by definition, a signal is a endless sequence of numerical values, and you're going to process all those values in the same way. You're going to get a stream of numbers coming in. You're going to do the same thing on every one. Audio signal processing is another example, right? So you're building a CPU to go in a guitar effects processor, something to go in a stomp box for a musician. You know there's going to be this endless sequence of audio samples flowing in, and you're going to do the same thing on every sample. You're going to distort it or apply a reverb effect or whatever. There's not really much notion of conditional branching in signal processing. You're just running this same program. So pipelining works really nicely for that sort of application, and you probably have a whole load of it in your musician's stomp box or in your TV. Yeah, it gets difficult when you have branches, because the people later on in the pipeline have to assume something about the sequence of instructions before you know what's happening. So this is a classic branching hazard. Okay, so you have to look at this in the right way. Sometimes pipelines can feel a little bit backwards. That's normal. This worker is processing the oldest instruction. Okay, as you move backwards in the image, you're looking at instructions further on in the program that have just entered the pipeline. So what you have here is a conditional branch instruction. Okay, this worker has encountered a branch, and the branch says, if I've got a square widget, then paint it blue, otherwise paint it red. And the worker is doing that comparison now, okay? They're looking at the color and have just identified this is a blue widget. Now, the other workers have already started processing the following instructions. And in the way this program's written, if you don't do the jump, you're going to follow the red branch, okay? If you decide this thing is in fact blue, then you're going to jump to a different instruction. So you see, this worker has already started painting something red. And this worker has started fetching the red paint, okay? That's like your fetch, decode, execute, approximately. So as soon as you introduce a branch, you have this problem because the workers further down the pipeline, they have to assume something. In this case, they've assumed that the program's going to take the red branch. We've only just figured out in the execution of this compare instruction that we should in fact be taking the blue branch. And so this process here of starting to paint something red is now going wrong. And that's called a branching hazard. There's a couple of other ways that pipelines can go wrong as well. So one is called a data hazard. So this is where we have a single memory location. So let's assume this shelf system is like the RAM of the computer. And you see this worker is about to do a store. They've just finished their instruction, or they're on the write back phase of a 4-stage pipeline. They are about to go and write the result of their work. They're going to take this workpiece and put it on shelf number 73. Okay, but this instruction, two instructions down, we've got a fetch worker is saying, I'll go and get the next instruction from shelf 73. Yeah? Now, if you're following this as a serial program, the intention is that this instruction should have executed first. This workpiece should have been put on 73, and 2 instructions later, we're going to go and read from it, and we're going to retrieve that finished workpiece. But that's not going to work if we start fetching from shelf 73 at the same time as this worker is finishing their work and trying to write to 73. So you might get an incorrect version, you might get an old version, or even worse, you might get undefined behavior where both stages are trying to read and write at the same time. The other type of hazard is called a structural hazard or a resource hazard, and this is where 2 workers need to use some physical resource at the same time, such as an ALU. So in a traditional CPU, at least, you only get one ALU. And that ALU might end up getting used in different ways. So, for example, here our fetch worker. In some instruction sets, you get quite complicated load and store and fetch instructions. You might have an instruction that says, go and load from address 23 plus 74 as operands in the instruction. And so to do that, you have to go and engage your ALU because you've got to do this little addition in order to find out where you're actually talking about, where you're going to load an instruction from. Whereas the same ALU might get used for equality checking, for example. So again, we've got this compare instruction saying, is something equal to 0 or not? There's actually a different ALU function, right? So a really clever ALU might let you do addition and comparison at the same time. Most standard ALUs will only allow you to configure one thing at a time. So here you've got a conflict where 2 workers are trying to use the same calculator, the same ALU at the same time. So much of the time, pipelining is great, especially for these signal processing type applications. And we'd like to have it, but we need to be aware that there are these few cases, and usually they're quite few and far between. But when they happen, you have to detect them and you have to do something about it. Otherwise, the execution of your program will not be correct. So here are some basic approaches called hazard handling strategies or mitigations. So most basically, you can dump the whole problem on the user. You can say, we architects are providing this system. Here you go. By the way, if you happen to call 2 instructions in a row that hit on the ALU, it might not work. So don't do that. Yeah, you just put a warning sticker on your CPU and say, make sure you don't have 2 or 3 instructions close to each other that are likely to lead to any of those situations. for actual human programmers, like games programmers of the 1980s, that is not a good situation. You don't really want to entrust a human with that. If your user is a compiler writer, this is actually not so bad. Yeah, you could imagine writing your compiler, and you only ever have to do this once. You just make sure the compiler isn't going to generate code with two instructions next to each other like that, and then the end user of a high-level language doesn't have to worry about it anymore. So, slightly more advanced form of this is to put in what are called NOPs, or null operations. You might add a special instruction to your instruction set that just does nothing. All it does is occupy a cycle of the CPU. So if you provide instructions like this, if your programmer has given you two instructions in a row that are in conflict, so that could include a branching problem, or it could include a data problem or a resource problem. You could either ask the user to do it themselves. You could just say, go and put a NOP instruction in between those problematic instructions, or maybe you need a few NOP instructions to clearly separate out the CPU cycle. Or equivalently, you can have a word with the compiler writers and ask them to do it. So a compiler writer can quite easily inspect the assembly code they've just generated and look for each group of 4 instructions in a row. And if there's a problem, they can put in a bunch of NOPs around it. Yeah, yeah. So this is called stalling or bubbling. Yeah, it's going to make the code run slower. If you're deliberately telling your CPU to do nothing on those cycles, execution is going to slow down. The theory is it only happens occasionally. Typically, you get these problems from loops. Okay, most programs have a bunch of loops in them, and most loops they'll spend most of their time in the loop. You might have 1,000 instructions in the loop, and then there's a little bit of code at the bottom that checks for the branch. Should I go back or should I fall through? And so you're going to get the acceleration on those 1,000 instructions, and you're just going to take a little speed hit at the end if it's done carefully. Some other approaches are to do the work. So you allow this kind of thing to happen. You allow these guys to start painting it red, and then you detect later that the red version is not needed, and you might just go back and do it again. So this is like stopping the production line and rewinding it. You're going to run the conveyor belt backwards a couple of steps and do the work again. That can get a bit messy, right? So typically you're going to have to mess with the CPU cycle. You might have to change which tick you're currently on and go back and do it again. So it's in theory, that's easy to do. You have your counter here. Normally, your counter is just running from 0 to 7. There's nothing to stop you as an architect from overwriting the counter. You might be on tick 5. You might just go and set another input that just resets the counter back to 1. You say, we've detected something's gone wrong. Someone started painting something red that they weren't supposed to do. Go back to tick 1 and do it the other way. Again, that's going to delay the execution. Or if you have lots of silicon available, which we do nowadays, the major challenge of modern architecture is figuring out what to do with all this extra silicon, right? We can't make the clocks go any faster, but we still have more and more silicon showing up through Moore's law for density. So there's this huge push, and GPUs are the extreme version of it. There's this huge push to use more silicon to do clever stuff rather than faster clocking. So in eager execution, you execute both branches at the same time. So this will usually entail physically making 2 copies of everything on the CPU. So we might print 2 ALUs on the same chunk of silicon, and one ALU is going to go off and add 3 and 4, and the other one adds 5 and 7, and you can do both until the compare operator's figured out which way it actually wants to go. So this might be seen as wasteful of silicon. You're basically going to double the size of your CPU doing everything twice when a branch comes along. But if you go this way, then you don't have to take the speed hit of stalling or redoing stuff. So more advanced hazard mitigations that we see in current CPUs can include prediction. So in a predictive CPU, we're going to try and guess which way a branch is going to go before we've actually computed it. And that sounds kind of impossible, right? Your program says compare the register with the number 0. If it equals 0, then go this way. If it doesn't equal 0, go that way. How can you guess in advance before you've actually done the comparison which way the branch is going to go? So it turns out in many cases you can make a good guess. You're not always going to be correct, but you can be 95% accurate, maybe 99% accurate. The reason is most branches are in fact taken. This is because most branches arise from loops in high-level programs, and usually in a loop you want to go around the loop several times. Okay, it's rare to have a loop that only goes around once. Sometimes it will just go around once, but most people who write loops intend them to go around several times, and in many cases that could be thousands or millions of times. So statistically, this is done through statistical analysis. You run your assembly code, your machine code, through simulations of CPUs, and you log what happens to it. You can just count how many times does a branch get taken, or how many times is it not taken. And from that kind of statistical analysis, you'll see you'll make a pretty good guess whenever you see a branch if you just assume that it is going to be taken, because it's probably come from a loop. So you can usually combine this with, say, the redoing work approach. In the 1% of times that it goes wrong, you just throw that work away, and you have to slow the pipeline down and redo something. But most of the time, you're going to be okay. Some high-level languages, especially C family languages, will allow the programmer to drop hints about which way the loops are going to go. So if you have a loop that is intended to run a whole load of times, most of the time, you can put that in a C language. It might be called a pragma. You might have seen these special comments called pragma. Those are not part of the program itself, but they're intended to give hints to the compiler about how it might want to execute things. So if you have a loop that is intended to run many, many times, you say so, and that will encourage, or more importantly, if it's not intended to run many times, you say that, and that'll kick the predictor to go the other way. Or as architectures have got much more fancy, we've started to see a lot of statistical analysis and even machine learning go into the architectural level now. So if you're running, at least if you have a modern AMD chip, there's probably a little neural network in there built out of hardware that is learning on the fly. It's learning which way did this loop actually go every time we executed it before. Early versions of this were just simple statistical models. They just analyze where the loop is in memory. Have I seen this loop before? And simply keep a statistical trail of 90% of times I've been at this memory location doing a fetch, I've ended up doing the loop or not doing the loop. Nowadays, you'll see these very advanced machine learning predictive models that look at all the factors, the states of the registers, the state of recent executions, and do as much inference as they can, because we have basically unlimited silicon available to do this kind of thing. We've got these huge chunks of silicon, and they seem huge as the transistors get smaller and smaller. We can't make them go faster. You might as well use a huge chunk of silicon to implement a hardware network to try and predict which way your branches are going to go, because there's nothing better to do with it, basically. So that's pipelining, okay? So pipelining means looking at fetch, decode, execute, or whatever other steps of your pipeline you have, maybe up to 37 slicings nowadays, and trying to do many of them at the same time. A more advanced form of pipelining that you will again see in a more modern CPU is called operand forwarding, and this is where you allow some information to be transmitted forwards through the pipeline. So you usually, if you're in a execution step, for example, you've only got access to information about the execution. You're assuming everything that's been done before has been done, and nothing from the future has been done. In an operand forwarding, you let different stages of the pipeline peak at each other's states. So basically, that means you put a whole load of extra wires into your architecture, and you take any information that could be predictive about what's going to happen in the future, and you send it on to those instructions further down the pipeline. And again, this is a way to help predict which way things are going to go. You know, if you're comparing a number to 0, maybe you haven't actually reached the stage of doing the comparison yet, but that register still has a state. It might already be 0. It might have been set 0 from a little while ago. So you might just send that down the pipeline as a hint for later stages to see what is going on. And even more advanced, you reach out of order execution, known as OOOE. Out of order execution is a more parallel version of a pipeline. In a pipeline, you're doing maybe 5 things at once, but there's still this notion of a series of execution. There's still clearly one instruction at a time that is passing through the pipeline. You just have 4 or 5 workers looking at it together. In out of order execution, you go beyond that and you try to process entire instructions in parallel with one another. That means a whole execution of an instruction can be going on alongside an execution of another instruction. And this works in cases where you have lots of instructions that are independent of one another. So let's consider this program here. Okay, this looks like a very RISC-style program. RISC-style programs just have triples of very simple instructions, and normally they have 3 registers at a time. Okay. So in this program, I've coloured in the register names to help us see what's going on. Okay, you can see we're doing all the computation inside registers. There's no memory access here. We've done some division. We've taken registers 4 and 7. We're storing the result of that in register 1. Here we're doing some addition. Now notice this addition requires the first instruction to have completed, right? So you can't run this instruction until you've finished running the one before, because you need the result from R1. So we're going to take that and we're going to add it to register 2, and we're going to store the result in register 8. Now this instruction, this is just incrementing register 5. Now you notice this is different from the previous one in that it doesn't depend on any of the others. Okay, this instruction could potentially be run at the same time as this pair of instructions up above it, because it doesn't rely on any of their results. If this instruction was doing register 5 plus register 8, for example, you would then have to wait for instruction 2 to have completed. And in particular, that means you've then got to wait for instruction 1 to complete. But as it doesn't depend on anything red or green, we could potentially run this at the same time as the first 2. Likewise, instruction 4 doesn't depend on anything. Whereas instruction 5, this depends on a lot of things. Okay, this depends on instruction 3 finishing, because you need that blue register 5. It also depends on instruction 4 finishing. So you can't start executing this until you've done everything before it. And likewise, instruction 6, you have to wait until you've got the green one and the purple one. Okay, now we can take a little window of code, and this is typically done with a smallish window. Maybe you consider about 10 or 12 instructions in a moving window that slides down your code. So a bit bigger than a regular pipeline, but not huge. So we're going to look at this window of code. In this case, we've just got 6 instructions, and in hardware, we might design this in Logisim. We're going to design a little hardware algorithm that analyzes the dependencies between these instructions. Effectively, they're going to do what I just showed you. They're going to color in all the registers, different colors, and they're going to trace back which colors do I depend on. And so that algorithm will produce something a bit like this. You can see instruction 6 depends on register 8 and register 4. Okay, and those are last updated in instruction 2 and instruction 5. Yeah, there's 8 and 4. So you can't start running 6 until you've done 2 and 5. Instruction 2 relies on instruction 1 having completed. Instruction 5 relies on 3 and 4 completing. And instructions 1, 3, and 4 don't rely on anything. So that means you could try executing these 3 instructions simultaneously. Okay? You're going to need a lot of extra silicon to do that. If effectively, you need 3 almost independent CPUs. This isn't a multi-core architecture, but it has a lot of the same components replicated. Yeah. So these 3 instructions, that they'll still take a full CPU cycle to go around, but in that cycle you're getting 3 instructions done rather than just 1. Yeah. Yeah. So this is almost like having 3 CPUs. It's not a multi-core system. We'll talk about multi-core later on, but you're going to need to replicate a lot of stuff. So if you take that Manchester Baby design in Logisim, for example, you're going to need to replicate the ALU 3 times and replicate the control unit and actually replicate most of it. It's almost like having 3 complete CPUs sitting there. So yeah, look, this is how the program would normally execute. And notice, by the way, this is a division. Division is typically a slow operation. If you try and write a divider in Logisim, it will typically require several clock cycles to do a division, whereas addition and multiplication and subtraction are much faster. So look, that division normally takes quite a lot of time anyway, because it's inherently hard. So normally you do that, and then you do 2, then you do 3, then you do 4. When you're doing out of order execution, you're going to do something like this. So you've created your data flow graph, you've figured out what can I do in parallel. And here, in this case, I'm going to run 1, 3, and 4 to start. When 3 and 4 have finished, I can make a start on 5. Now remember, 1 is that division. It takes longer than everything else, so that's actually the bottleneck in this case. So once 1 has finished, then you can go and do 2. And then when 2 and 5 have finished, now you can go and run 6. And you can see this takes less time than the in-order execution over here. So that's pretty complicated, right? You're really changing the program itself. It's almost like you're running a small optimizing compiler inside the CPU. It's also been the source of some major security risks recently. If you've heard of these vulnerabilities in your CPU called Spectre and Meltdown, those are vulnerabilities that attack this system. So an attacker can write code which starts to get executed before you've decided whether or not it's supposed to be executed. Yeah. So I mentioned earlier operating systems features in the CPU. These are processes that check which privilege mode you're in. Am I running as the operating system or as the user? And Spectre and Meltdown work by throwing in these extra instructions that start to execute while those decisions are being made. So the first instructions are just figuring out, am I supposed to be in privilege mode or user mode? And you just get 1 or 2 extra instructions starting to execute in that early time. And 1 or 2 instructions can be just enough to go and load the user's password from an area of memory that they're not supposed to be accessing. Okay, so we've seen a lot of complexity introduced in this lecture, right? We've seen how instruction sets can become very complex. We've seen this process where the software guys keep phoning up the architects and saying, can you put this extra feature in your CPU for us? On the other hand, we've seen how execution of instructions can become very complex through pipelining and out-of-order execution. And there's generally a tension between those 2 approaches. If you keep throwing extra features in for your users, it gets harder and harder to do clever pipelining and out-of-order execution. And this is the basis of the famous CISC versus RISC debate. Okay, CISC and RISC are 2 opposing philosophies of CPU design, standing for complex instruction set computers and reduced instruction set computers. So in a CISC design, you're going to keep answering the phone to the software guys, and every time they say, can you add this extra feature, you say yes, and you use all this extra silicon now available to put in more and more, typically more and more instructions. So that includes different flavors of instructions. Like we saw this morning, 4 different ways of making an add instruction, depending on whether the operands are from registers or from memory or from indirect. In a CISC architecture, you'll say, bring it on, let's have all those different flavors of the add instruction, and you might end up with 20 different forms of addition, depending on how you set up the operands. So another aspect of CISC is creating single instructions that become very complicated. So a user might phone you up and say, I'm building a multimedia system, I'm going to put this thing in a television, in the back of a Sony smart TV, and it's going to spend most of its time doing MP4 decoding. And MP4 decoding has certain mathematical operations to do with Fourier transforms in particular. Please can you put in a load of extra silicon to do Fourier transforms so that my smart TV can go really fast? And a CISC designer is going to say, yes, of course we can. We've got all this spare silicon, we're going to use it to do your niche thing. And so typically you end up with very customized hardware. You end up with instructions that are complex themselves. That includes instructions that require more than one clock cycle to complete.
It sounds like is it more common for computers to have both access and risk, or is it that they use
Yeah. So, okay, in practice, this is a bit of a cartoon, right? In theory, when you're writing a textbook or giving a lecture, it's a really nice way to set up a debate between 2 opposing philosophies. In practice, it's very rare to find a pure CIS system or a pure RISC system. You will tend to find most systems favor one or the other, but they will sometimes adopt features from the other side. Typically, you'll find CISC on your desktop and in your servers and anything that's connected to the mains, and you'll find RISC in your pocket and anything that runs off a battery. And that's because CISC is more complicated. You need a lot more silicon, you need a lot more transistors, you need more power, and you therefore need to connect it to the mains. Yeah, there's endless argument about what exactly is CISC and RISC, and over whether any given architecture is in fact purely RISC or purely CISC. So a defining feature of CISC is that you get these complex instructions that do load and storing along with whatever else they're doing. So in a RISC architecture, you'll have a separate load and store instruction and a separate arithmetic instruction. In a CISC architecture, it's all done in a single instruction. And the result of this is that CISC programs are small because you have many different instructions available. You can do a lot of work in one instruction on CISC. So traditionally, CISC programs were preferred by human assembly programmers because they could write much more readable pieces of code and do a lot more work in each instruction. RISC programs are really boring for human programmers. They just consist of streams of really simple instructions that normally just do loading and storing and adding and not much else. And they have these very homogeneous rows of 3 registered triples. So they're not nice for humans to read, but they're much nicer for compiler writers to work with because there's not as much complexity in the instruction set. They're also much nicer for people making pipelines and out of order execution because you keep the instruction set simple. That means you don't have to think about all these special cases. There's fewer ways for a pipeline to break, for example. So look, this is the main characteristic of CISC. You get instructions like this. This is saying multiply the content of memory location 23 with location 52. This is a 2-dimensional organized memory, so this is 23 and this is 52. Now, think about it. This is actually a lot of work getting done in a single instruction. Okay, to execute this, a CISC processor first has to bring in a copy of address 23, bring that into a register. Then it brings in a copy of address 52 to another register. Then it multiplies them together by connecting them to the ALU. And then maybe it's going to take the result of that and write it back to a memory location, usually the first memory location that you gave. So that's actually 4 different steps that are all combined into a complex instruction. But for a human programmer, that's nice, because they only have to write one instruction. When you create all the different flavors of that, so like we saw with addition, you might have 20 different multiply instructions to do with where are the operands coming from. Are they in registers? Or are they in memory? Are they constants? Are they indirect addressing? All that stuff. So every instruction in CISC tends to emerge as a set of maybe 20 different flavors of that instruction. At the same time in CISC, you have this constant stream of people phoning you up and saying, can you put in this special thing for my cryptographic primitive, or for my multimedia codec, or for my floating point system? Floating point is a huge can of worms for making many, many more instructions. So for the Manchester Baby and the 6502, I could show you the complete instruction set on one slide. Okay, this is the complete instruction set of this desktop PC. If you're using an Intel or AMD, that architecture is called AMD 64. They're the same, the Intel architecture and AMD, they track each other. This is the instruction set for AMD 64, okay, and it's 5 large and quite expensive physical paper volumes. And you'll see volume 1 is for user-facing instructions. You get a whole volume full of those restricted mode instructions. So this volume is for the people who write the Linux kernel, or the people who write Windows or macOS. These are instructions that can only be run from that mode. Then you've just got a whole book of general purpose extra instructions. Then you've got a whole book of floating point and media instructions. Then you've got another book full of 128 media instructions. So no human being can really understand the full instruction set of a modern CISC CPU. Over 3,000 available instructions. And as a result of this, even the compiler writers often don't use them all. It's common now for CISC architects to provide all these whizzy features, but the compiler writers just can't keep up with it, and so they tend to write compilers using the more basic features, especially the features that are common across many different CPUs, so the compiler can be easily ported between machines. So it's very common. For example, Netflix will phone up Intel and say, this is the thing our app spends most of its time doing to do this video decoding. Can you put in a whole bunch of extra media instructions? And AMD, it's actually AMD who sets the specs. We'll talk about the history of this later in the module. AMD will say, yes, sir, we'll go and add an extra chapter to this book full of your instructions. Now, the compiler writers over at Microsoft or over at GCC for the open source C compiler, they're not hugely motivated to go out and track every little detail that AMD have added for Netflix, right? They're generally more interested in volume 1, because volume 1 is roughly portable to other architectures, and it's less hassle for them to use these simpler instructions. So when you get CISC architectures, you'll typically find they need to employ an in-house compiler team, because nobody else wants to work with their architecture to write a compiler. So AMD and Intel will have their own compiler writers who are paid to know what all this stuff is and to figure out how to use it when they compile your user-facing program. So that's CISC, associated with these kinds of companies. RISC is the opposite. RISC is supposed to be lean and mean. You keep the instruction set as small as you can. That means a program has to get compiled into many more instructions. So RISC executables are much longer than CISC executables, but they're made up of these small, simple instructions. And that means your CPU can be physically smaller, it can be physically lower power, and is therefore very well suited to the computer in your pocket rather than the computer on your desk. The defining feature of RISC is this is how you do arithmetic. Okay, so what was one instruction in CISC has become 4. You do 2 loads, bring those things into registers, then you multiply them inside the CPU. You see here's a RISC triple. We're multiplying those 2 registers, putting the result in this register, and then we're going to store the result back in memory. That's a classic RISC feature. And this is especially nice if you can get all your instructions to execute in the same amount of time. If everything fits within the same cycle, it's a lot easier to do pipelining and out-of-order execution. And so CISC and RISC styles, they can occupy the same amount of silicon. CISC will fill it up by putting in loads of WYSI features and instructions. RISC will fill up the silicon by doing clever things with pipelining and out-of-order execution. So CISC is nice for human programmers, assembly programmers. RISC is nice for human compiler writers and is associated with these organizations. So that was a tour through more modern CPU design. Please try and do your reading every week. Do some optional reading. Here are some educational video games. If you like games, they'll teach you a bit about assembly programming. Come back next week. We'll start talking about I/O and memory. See you then.